Hey, what is up, guys? Can you guys hear me? If you can you please put in the chat? Alright, so what is up, guys? Today we will be going over the 2016 AP Chemistry FRQ. If you want the FRQ, it is in the chat right now. There's a link to the College Board one. I suggest you guys print it out if you haven't done so before. And we will start in just a few minutes. Wait for a few more people to join, and we will start. Alright, so let's get to the test now. Alright, so today we're going to be going over the 2016 AP Chem FRQ. We'll be going through all the questions. I'm trying to do a Pomodoro thing. Actually, it's not working, so I'm going to just get rid of that. But yeah, so we're going to start now. So let's just start with question 1. A student investigates the enthalpy of a solution for 2 alkali metal halides, lithium chloride and sodium chloride. In addition to the salts, the student has access to a calorimeter, a balance with a precision of plus or minus 0.1 grams, and a thermometer with a precision of plus or minus 1 degree Celsius. To measure the enthalpy of the solution for LiCl, the student adds 100 grams of water initially at 15 degrees Celsius to a calorimeter and adds 10.0 grams of LiCl solid, stirring to dissolve. After the LiCl dissolves completely, the maximum temperature reached by the solution is 35.6 degrees Celsius. Calculate the magnitude of the heat absorbed by the solution during the dissolution process, assuming that the specific heat capacity of the solution is 4.18 joules per gram degree Celsius. Include units with your answer. Alright, so for part number 1 or part I of A, what we're going to use is Q is equal to MC delta T, where Q is heat absorbed in joules or kilojoules, where M is mass in grams, where C is specific heat capacity. I'm not going to write capacity, but specific heat in joules per gram times degree Celsius, and where delta T is change in temperature. Which is in degrees Celsius or Kelvin. So what we're going to do is we're going to plug in what we know. What we know is we're looking for Q, heat absorbed. So this is what we're looking for. What are we going to plug in for M? We start with 100 grams of water, and the student adds 10 grams of LiCl. That means we have a total of 110.0 grams of mass in the calorimeter. Then the specific heat capacity of the solution is 4.18 joules per gram times degree Celsius. So we're going to write that for a specific heat capacity. And finally, the delta T, which is the change in temperature, is given here, where we start with 15 degrees Celsius and the maximum temperature reached by the solution is 35.6 degrees Celsius. So what we'll do is we'll do T of final minus temperature of initial temperature is equal to delta T. So the final temperature here is 35.6 degrees Celsius, and the initial is 15.0 degrees Celsius. That means delta T is equal to 20.6 degrees Celsius. And we can plug that in here. Now we're looking for Q. So let's just multiply all these things together. 110 times 4.18 times 20.6 is, with sig figs, 9,470 joules, or you can write it as 9.47 kilojoules. And that's our answer to part 1 of question 1A. Now, question 2A. Determine the value of the enthalpy of solution for LiCl in kilojoules per mole of reaction. So what we're going to do is we're going to first find the amount of moles there are, because that's going to be the denominator. We're going to divide the enthalpy in kilojoules over the moles of LiCl. So let's find that. We know that we have 10.0 grams of LiCl. So now let's convert that to moles. So how are we going to do that? We're going to get the atomic weight, average atomic weight. So 6.94 plus 35.45 is 42.39. So we do 10 divided by that. We need 3 sig figs, so we're going to have 0.236 moles of LiCl. Now, how are we going to find the enthalpy of solution? The way we find this out is we know that change of enthalpy is equal to negative Q. So how are we going to find the change of enthalpy? We'll plug in the Q we got here and just multiply by negative 1. So our change of enthalpy is going to be negative 9.47 kilojoules. And now we can put that in our numerator, and we can put this amount of moles in our denominator. We get negative 9.47 over 0.236, which is equal to negative 40.1 kilojoules per mole. And that is our enthalpy. All right. So, right now, does anybody have any questions? All right, seems not. So let's go on to the next question. To explain why the enthalpy of the solution for NaCl is different than that for LiCl, the student investigates factors that affect the enthalpy of solution and finds the ionic radius and lattice enthalpy, which can be defined as the change in enthalpy associated with the separation of solid crystal into gaseous ions contribute to the process. The student consults references and collects the data shown in the table below. So what we're given here is the Li plus ion radius, ionic radius, and the Na plus ion radius. We know that the Na plus ion has a bigger radius than Li, and we already know this because of periodic trends. And we can see that since Na is in a period under Li, it has a higher principal energy level, it has a bigger radius. So that's just an observation I made right away. So let's go to 1b. Write the complete electron configuration for the Na plus ion in the ground state. So let's go to our periodic table real quick. Since we're doing the ground state, we can't include any noble gases here, like any, and then we can say 3s1, which would be wrong, by the way, and I'll get to that in 1 second. So what we have is H, and He should be here when we talk about electron configuration, but since it's a noble gas, it's on the periodic table, it's here on the periodic table. But we count this in the 1s group, so this would be 1s2, Li, Be, we pass that 2s2, Bc and oxygen, fluoride, neon, we pass that 2p6, and then Na over here is 3s1. But remember what the question is asking for. It's not asking for Na, the electron configuration of Na in its ground state. It's asking for Na plus, meaning that Na lost an electron. So that means we're going to take away one here. So our final electron configuration is going to be 1s2, 2s2, 2p6. And that's why I said, earlier that we can't do the any 3s1. It's because it's Na plus. It lost an electron, so it'd just be Ne. But that does. I don't think they ever show an electron configuration like that on the AP exam. All right. So question 1c. Using principles of atomic structure, explain why the Na plus ion is larger than the Li plus ion. Well, here we could write something about higher principal energy levels. I would probably write that. Sorry for my loud typing, by the way. It's just my keyboard. But I would write something like So yeah, when we talk about higher, I think this is what I would write on the test. But the reason being that uh, when uh, when we're looking at two elements with one having a higher principal energy level, the electrons in the electrons on the element with a higher principal energy level are on average farther from the nucleus than the ones with a lower. So if we were to draw like the Li plus model, it would be something like this. So let's say this is the nucleus. This is the electron cloud. So this would be Li, and Na would be something like this. Na plus. Sorry, should have wrote that. Yeah, it would be something like that. All right. All right. Next question. 1D. Which salt, LiCl or NaCl, has the greatest lattice enthalpy? Justify your answer. All right, let's compare LiCl and NaCl. But first, we have to figure out how do we compare lattice enthalpy. We could look at Coulombic attractions. We know that force is proportional to Q1 times Q2 over R squared. Q1 and Q2 being the charges of the two particles, and R squared being the radius or distance between the two particles. So when we look at this, this just means that as the charges increase, as the charge of the two particles increase, the force increases. So as Q1 and Q2 increase, then force increases. But as radius decreases, force increases. And as radius increases, force decreases. They're inversely proportional. So let's compare them now. LiCl and NaCl. Li plus Cl minus. We're going to multiply their charges. Plus 1, negative 1, that's negative 1. Now NaCl, Na plus Cl minus, plus 1 times negative 1 is negative 1. They have the same Q1, Q2. So that's just irrelevant now. Now we only look at the radius. And as we said earlier, the Li plus ion has a smaller radius than the Na plus ion, meaning that that LiCl is going to have a greater lattice energy. And we could talk about Coulombic for the justification. We could talk about Coulombic attractions and the difference in radii. All right. So let's go to 1E. Below is a representation of a portion of a crystal of lithium chloride. Identify the ions of the representation by writing the approximate formulas Li plus or Cl minus in the boxes below. Well, right now what I'm looking at is I see big atoms, and I see small atoms, or to be exact, ions. How are we going to tell which one's bigger? We always know that anything that has a negative charge is going to be bigger than anything with a positive charge to some extent, or on average, or in general. So we know that in this case, Cl minus is going to be the bigger ions, and Li plus is going to be the smaller ions. So we can graph it like this. And that's it. All right. So now let's look at F. The lattice enthalpy of LiCl is positive, indicating that it takes energy to break the ions apart in LiCl. However, the dissolution of LiCl in water is an exothermic process. Identify all particle interactions that contribute significantly to the dissolution process being exothermic. For each interaction, include the particles that interact in the specific type of intermolecular forces between those particles. Well, again, we know just off the bat that this is going to be an exothermic reaction because the enthalpy of the solution is negative. So we already know this is going to be exothermic, but it's asking for when it's dissolved in water, what are the intermolecular forces between the particles? Well, it's Li plus, it's interacting with polar H2O molecules. And Cl minus as well is also reacting with polar H2O molecules. And since these are polar, it's an ion reacting with a polar molecule. These are just going to be ion dipole interactions. Oops, sorry. Yep. And that's it. All right. We'll take a quick break for questions. So if you guys have any questions, just put them in the chat. All right. Okay, looks like nobody has any more questions. So let's go to question number 2. All right. So question number 2. A student designs an experiment to study the reaction between NaHCO3 and acetic acid. The reaction is represented by the equation above. The student places 2.24 grams of NaHCO3 in a flask and adds 60 ml of 0.87 molar acetic acid. The student observes the formation of bubbles and that the flask gets cooler as the reaction proceeds. Identify the reaction represented above as an acid-base reaction, precipitation reaction, or redox reaction. So what we can do here is actually pretty simply just use process of elimination. Let's look at precipitation reaction real quick. There are no precipitates in this reaction. That automatically cancels this. We can't even consider this because of that. So that gives us 2 choices left. Let's look at redox reaction. In this reaction, the charges of the charges are not going to change, meaning that there's no redox reaction happening. So that's going to cancel out. So we're going to be left with acid-base reaction. But if you guys wanted to check, the weak acid here, acetic acid, reacts with the weak base HCO3. And with the acetic acid, it's going to donate the proton to HCO3. So we know that this is an acid-base reaction. All right. So now let's go to 2. Based on the information above, identify the limiting reactant. Justify your answer with calculations. So let's look at what we have. The student places 2.24 grams of NaHCO3 in a flask and adds 60 ml of 0.87 molar. So we want to convert this to moles. We want to see which one is the limiting reactant. We're given 2.24 grams of NaHCO3. Let's convert that to moles. By the way, if you notice, there's a 1-to-1 mole ratio in the reactants. So this is going to be easier for us because we don't have to like multiply anything by the coefficient. So 2.24 grams divided by 22.9 plus 1.008 plus 12.11 plus 48. So about 83.919 grams is equal to 0.0267 moles of NaHCO3. And that's the amount of moles we have for HCO3. So now let's find how many moles we have for acetic acid. We're given 0.87 molar acetic acid. But what is the relationship between moles and liters? Because we're given liters here. We know that molarity is equal to number of moles in the reaction over liters of solution. And we want to find out what N is. And we're given M and L. We can manipulate this equation so that N is equal to M times L. And then we can plug in what we're given. 0.875 molar times 0.06 liters, because we are given 60 ml. And that's going to be 0.06 liters. So at the end, we get 0.0525 moles of acetic acid. Now, it's not asking us just to find how many moles we have. It's asking for the limiting reactant. And the limiting reactant is going to have the least amount of moles. Thus, our answer here is going to be NaHCO3. All right. And we don't have to make a whole sentence or anything because we're showing our calculations. So we justified it. All right. 2C. The student observes that the bubbling is rapid at the beginning of the reaction and gradually slows as the reaction continues. Explain this change in the reaction rate in terms of collisions between reactant particles. Well, let's think about it. Let's say we have a box and we have a certain amount of particles, right? I'm just going to draw it quickly, right? And it's moving all over the place, right? They're all like scattered. They're going left, right, up, down, side to side, right? They're hitting each other. As the reaction continues, and the concentration decreases, as said, the number of collisions are going to decrease too, right? So that's essentially going to be our explanation for C, that as the concentration of the reactants, sorry. As the concentration of the reactants decrease, let me reword it, I'm sorry about that. As the reaction progresses, the concentration of the reactants decrease. This makes the amount of collisions decrease as well. Yeah, sorry about my loud keyboard, guys. But yeah, that's essentially something you want to write for C. All right. So let's get to 2D. In thermodynamic terms, a reaction can be driven by enthalpy, entropy, or both. Considering that the flask gets cooler as the reaction proceeds, what drives the chemical reaction between NaHCO3 and acetic acid? Answer by drawing a circle around one of the choices below. And part 2 is telling us to justify our selection. So looking at the choices, we know it's going to be entropy only. And I'll explain why right now. Since we know that G naught is equal to change in enthalpy naught minus T S naught, and we know the reaction is endothermic, meaning H has to be positive. So we need to make sure that this reaction is spontaneous, or in other words, what College Board likes to use, thermodynamically favored. But we know since the reaction is endothermic, since it says here that the flask gets cooler, that means it's endothermic. That means H is going to be positive. And that's not going to help us. We need to have we have to have G not negative. So the reaction is not driven by enthalpy. So that already, if one crosses out, then the other crosses out, and we already know entropy only. But also, we can notice that since there are no gases in the reactants, and one of the products is a gas, that means that S naught has to be positive, which makes G negative, because negative TS. And negative times a positive is, of course, a negative. And that's how we answer. I'm not going to really make an answer for this right now, but that's essentially what you need to know, and you guys should be able to build your own answer based off of that. All right, so let's do 2E. The HCO3 minus ion has 3 carbon to oxygen bonds. 2 of the carbon to oxygen bonds have the same length, and the third carbon to oxygen bond is longer than the other 2. The hydrogen atom is bonded to one of the oxygen atoms. In the box below, draw a Lewis electron dot diagram, or diagrams, for the HCO3 minus ion that is or are consistent with the given information. So right off the bat, I know this is going to be a resonance structure. And you'll see why in a second. So let's draw this. So there's 3 carbon oxygen bonds, and okay, yeah. So it's going to look something similar to this. And what we're going to have here is we're going to have one double bond here. We're going to minus, and then this is going to have a resonance structure of the double bond, instead of to the right, going to the left. It's not a great picture, sorry about that, guys, but yeah, this is how we're going to draw it. Alright, so let's go to F. A student prepares a solution containing equimolar amounts of acetic acid and NaC2H3O2, which is just sodium acetate, I think. The pH of the solution is measured to be 4.7. The student adds 2 drops of 3 molar HNO3 and stirs the sample, observing that the pH remains 4.7. Write a balanced net ionic equation for the reaction between HNO3 and the chemical species in the sample that is responsible for the pH remaining at 4.7. So we know there's going to be a buffer solution. And what we can do is we can write acetic acid, or acetate, my bad, acetate plus this HNO3 ion is going to yield into acetic acid plus H2O. Pretty sure there can be 2 answers also. You can also do acetate, I'm going to write over here actually, acetate plus H plus ion yields acetic acid. That's how you solve problem F, 2F. All right, any questions so far? All right, so I'm gonna take a quick water break, and I'll be right back, and we'll continue doing 3, 4, and we'll finish the test, definitely. We'll probably do 3 more pages, maybe 1 more break, and then we'll finish the entire test. All right, guys? I'll be right back. Alright guys, we are back. Um, let's get right back into it. Alright, question number 3. To determine the To determine the molar mass of an unknown metal, M, a student reacts iodine with an excess of the metal to form the water-soluble compound Mi2, as represented by the equation above. The reaction proceeds until all of I2 is consumed. The Mi2 solution is quantitatively collected and heated to remove the water, and the product is dried and weighed to constant mass. The experimental steps are represented below, followed by a data table. So let's look at this. So they add the M here. They find the weight of the beaker, so we can find out the weight of the M by subtracting these two. And then they add I2, so we can figure out the weight of that by subtracting these two. Then they add H2O. The reaction occurs, it dissolves. There's leftover M here. This is the solution is Mi2. Then they collect it, they heat it, and then they reheat it. All right. So let's go to 3A. Given that the metal M is in excess, calculate the number of moles I2 reacted. Well, as said earlier, we can find I2 by just doing 127.570 minus 126.549. That's going to give us 1.021 grams. And remember, it's asking for moles, so what we're going to do is we're going to do 1.021 grams over its atomic mass. The atomic mass of iodine is going to be 126.9 times 2, 253.8. Go back here, 253.8. And we get 0.0040 moles. 4023 moles with sig figs. That is A. Now B, calculate the molar mass of the unknown metal M. So what we can do here is with our 1.284 grams of Mi2, which is constant, we can subtract that from 1.021 grams of I2 that we got here to find out the mass of M. We get 0.263 grams of M. And again, it's asking for the molar mass. So what we're going to do is we know that since the reaction is M plus I2 yields Mi2 and it's a 1-to-1 mole ratio, that means the amount of moles in M is going to be the same amount of moles that I2 has. So we know that M is 0.004023 moles. And we're going to find the atomic mass by dividing the amount of grams of M over the amount of moles. And you can tell this because the atomic mass of something is always gram per mole. So when we do that, we get 65.4 grams per mole. And that is our atomic mass. Alright. Now, C. This is going to be an explanation question, so I'm going to be ready to type. Propose an experimental test the student could perform that could be used to support the hypothesis. The student hypothesizes that the compound formed in the synthesis reaction is ionic. Explain how the results of the test would support the hypothesis if the substance was ionic. So, what the student could do is probably he could do one of two things, or they could do they could dissolve the compound in water or melt it. And see if the solution conducts any electricity. And based on that, you would know that the ions would be there because the systems would be likely ionic. And for 2, the student could heat the compound probably until it melts or boils. And if it had a high boiling point / melting point, it is likely that the compound is, I'm going to write it up, compound is ionic. Right? So that would be your answer for 3C. One of those 2 things. Alright, let's go to 3D. The student hypothesizes that Br2 will react with metal M more vigorously than I2 because Br2 is a liquid at room temperature. Explain why I2 is solid at room temperature, whereas Br2 is a liquid. Your explanation should clearly reference the types of relative strengths of the intermolecular forces present in each substance. So let's look at the intermolecular forces in each substance. Br bonds with Br. Just looking at it, we know that it's going to be LDF, Lewis dispersion forces. And it's the same thing for I, because I just like drawing it out, but you can just see by looking at the compound, that I2 and Br2 have LDFs. So the reason that I2 is solid at room temperature is because that I2 is a bigger molecule than Br2, meaning that it will have a higher melting point, and it'll make the Lewis dispersion forces stronger, really, meaning that it'll have a high melting or boiling point. So that's why it's a solid at room temperature. So you could say something like I2, they both have LDFs. I2 is therefore it has stronger LDFs and has a higher melting point than Br2. This is why it is solid at room temperature while Br2 is a liquid. And you can write something like this for your answer. You should get full points for this. Alright, let's look at E. While cleaning up after the experiment, the student wishes to dispose of the unused solid I2 in a responsible manner. The student decides to convert the solid I2 to I- aqueous anion. The student has access to 3 solutions: H2O2, Na2S2O3, and Na2S4O6, in the standard reduction table shown below. Which solution should the student add the I2S to reduce it to I-? Circle the answer below, justify your answer, including a calculation of E for the overall reaction. So we know here we're going to have to do I2 plus 2E yields 2I-. This is going to have to be there. This is reducing. So let's look at H2O2 first. What we have to do here so that the reaction works is we're going to have to flip it over. So one second, let me just write this real quick. 0.54 volts. So if we have H2O2 yields O2 plus 2H plus 2E minus, we have E naught is equal to negative 0.68. Now, even though this reduces and this is and this oxidizes, and it's all fine and dandy, we have to realize that E naught, when we sum this up, will turn out negative, and we need it to be positive. E naught has to be positive, but here it's going to be negative, so we can't have this half reaction here. Let's try this one. S4062. S4062 minus plus 2E minus yields 2S2O3 2 minus. This is not going to work either because this also reduces, and you won't be able to sum those two up. So that's not going to work. So our final answer through process elimination is going to be this. But if we look at it, because we have to justify our answer, we have to switch these around. So this is going to be 2S2O3 2 minus yields S4O6 2 minus plus 2E minus, and that is 0.08. And that still allows the E naught to be positive. So this is going to be our answer. Now write the balanced net ionic equation for the reaction between I2 and the solution you selected in part E. Oh, well, this is super easy. I'm just going to write oxidizes here because just to show you guys. But this is super easy. We already have like our reaction. Cancel out the two E's. Then we have I2 plus 2S2O3 2 minus yields 2I minus plus S4O6 2 minus. And that's it. All right. So let's look for any questions real quick. Oh no. I realized that you guys were you guys able to see this? Sorry about that. Oh, sorry guys, I'm not sure if you guys saw that, but if you want to take a screenshot, you guys can look at this. I thought it was showing my screen. Hopefully you guys kept along with my voice. Oh man. Shoot. Alright, I think you guys can see this now. Alright. Well, now let's just get to number 4. So, phenol is a weak acid that partially dissociates in water according to the equation above. What is the pH of 0.7 molar C6 H5OH aqueous solution? So we know here that Ka is equal to products over reactants, all aqueous ones. So this is going to be over, since it's a liquid, since H2 is a liquid, we can leave that out, H5OH. And what we know is when we make an ice table, let's write out the reaction again. And let's ignore the H2O. We draw an ice table for this. We start with 0.7 molar of this. We have 0 of this because this is the start of the reaction. We don't have anything in our products. We subtract x, since there's only a 1-to-1 mole ratio for all of these. We subtract x here, add x here, add x. We have 0.75 minus x, x, and x. We can plug those back in and say that 1.12 times 10 to the power of negative 10 is equal to x squared over 0.75 minus x. Since Ka is so small, we can say that x is about 0. So we can just multiply 0.7. So let's just get rid of that x we had here. And now let's solve for x in the numerator. So 1.12 e negative 10 times 0.75 and the square root of that. We get x is equal to 9.2 times 10 to the power of negative 6 molar. Alright. Now, the question is not asking for the concentration of C6H5O minus or H3O plus, or even this, which would be really small. It would be a really small difference, like 0.74999, something like that. But it's asking for the pH. And X is the H plus conc here. And how do we find the pH? pH is equal to negative log of H plus conc. So we're going to write negative log of 9.2 times 10 to the power of negative 6. And when we put that in our calculator, we get 5.04. And that is our pH. Alright, so I'm just going to write this right here. Alright. Now for part B. For a certain reaction involving C6H5OH aqueous to produce at a significant rate, the phenol must be primarily in its deprotonated form, C6H5O minus aqueous. In order to ensure that C6H5OH aqueous is deprotonated, the reaction must be conducted in a buffered solution. On the number scale below, circle each pH for which more than 50% of the phenol molecules are in the deprotonated form C6H5O minus aqueous. Justify your answer. All right. So to figure out the pH of when a deprotonated form will predominate, we have to know that pH is greater than pKa. That's when a deprotonated form will predominate. And let's find out the pKa. The pKa is equal to negative log of Ka, 1, 2, times 10 to the power of negative 10. So we know pKa is equal to 9.95. So any pH greater than 9.95 will be deprotonated, will be the deprotonated form and will predominate. So any pH greater than 10, so we will circle, or greater than or equal to 10, so we'll circle 10 to 14, and that is our answer. All right, now we will take any questions. So sorry about the last one, guys. I thought I was streaming it. But hopefully you guys can just go along with my voice and go about that if you guys were having trouble with that question. Alright, looks like no one has any questions. So let's just get to question 5. Alright, so at high temperatures, the compound C4H6 reacts according to the equation above. The rate of the reaction was studied at 625 Kelvin in a rigid reaction vessel. 2 different trials, each with a different starting concentration, were carried out. The data were plotted in 3 different ways as shown. So we're giving a conc versus time graph, a natural log versus time graph, and an inverse conc versus time graph. And just looking at these graphs and looking at these things, these are like the integrated rate laws. graphs, and I can tell that this is 0th order, this is 1st order, and this is 2nd order. Just an observation I made before I even look at the question. This may help us go through this question even faster. So, 5a. For trial 1, calculate the initial pressure in ATM in the vessel at 625 Kelvin. Assume that initially all the gas present in the vessel is C4H6. So, let's look at the ideal gas law. We have PV is equal to nRT. And for the conc versus time, we have an initial of 0.2 molar. 0.02 molar. And that's for our trial 1. But in this equation, it asks for n. And how would we could convert this to moles, but something that would be really quick is if we divide V here, we get P is equal to N over V times RT. Remember that molarity is equal to N over V. So we can plug in P is equal to 0.020 times 0.08206 times 625 Kelvin. And we get P is equal to about 1.0 ATM. And that is our pressure for A. Alright, now B. Use the data plotted in the graphs to determine the order of the reaction with respect to C4H6. So, without looking at the graphs right now, the way we know that the order of the reaction is if the graph is linear. Once the graph is linear, we can tell by if it's inverse. The 0th order is going to be the conc versus time graph. The 1st order is going to be ln conc versus time graph. And the 2nd order is going to be the inverse conc versus time graph. So for B, let's look at which one's linear. And we can see that this is not linear, this is not linear, but this one mostly resembles a linear graph, and this is an inverse conc versus time graph, meaning that this reaction is in 2nd order with respect to C4H6. All right, now let's look at C. The initial rate of the reaction in trial 1 is 0.001 moles per liter times second. Calculate the rate constant K for the reaction at 625 Kelvin. So we only have this here. And what we're going to do is we're going to say that rate is equal to K times C4H6 squared, since it's 2nd order. And it's asking for K, and we have 0.001 mole per liter times second. So let's plug that in. Equal to K times 0.020, which is our initial for trial 1, our initial conc for trial 1, squared. And just doing algebra, we can figure out that K is equal to 2.5 liters per mole times second. Make sure that when you ever solve for K, you always are doing it with the units. And that's it. All right. So that's question 5. Any questions whatsoever? All right. So what we're going to do now is take another few minutes of a break, and we will come back to finish the test. All right. Cool. Alright, we are back. We are going to finally finish this. Alright. So, question number 6. The polyatomic ion C10H12N2OA4- is commonly abbreviated as EDTA4-. The ion can form complexes with metal ions in aqueous solutions. A complex of EDTA4- with Ba2 plus ion forms according to the equation above. A 50 milliliter volume of a solution that has EDTA4- aqueous concentration of 0.3 molar is mixed with 50 ml of 0.2 molar BaNO3 to produce 100 milliliter of solution. Considering the value of K for the reaction, determine the concentration of Ba EDTA2- aqueous in the 100 milliliter of solution. Justify your answer. Well, I'm going to type this one out. So, looking at K itself, we know that the reaction goes to completion. Based on that, we know that Ba2 plus is going to be the limiting reactant. Oh my gosh, I'm sorry for the typos. Right, so once we know this, the reactions is going to, for this, is just going to be 0.20 m divided by 2, which is going to be 0.10 molar. And this is because when the solutions are first mixed and before the reaction takes place, we just divide it by 2. And that's how we get our answer. Alright? So let's just write this as 6b. 6a, my bad. So now, 6b. The solution is diluted with distilled water to a total volume of 1 liter. After equilibrium has been reestablished, is the number of moles of Ba2 plus present in the solution greater than, less than, or equal to the number of moles of Ba2 plus present in the original solution before it was diluted? So I'm going to write this one out too, because we can just write something really quick and get the answer. So the number of Ba2 2 plus moles increases because of the increase of the percent dissociation. Percent dissociation as the solution dilutes. And that's our answer for B. It's really simple, and it looks kind of intimidating, but it's just as simple as that. Alright, now let's get to the final question, question number 7. A student is given 25 milliliter sample of a solution of an unknown monoprotic acid and asked to determine the concentration of the acid by titration. The student uses standard solution of 0.11 molar NaOH aqueous, a burette, a flask, an appropriate indicator, and other laboratory equipment necessary for the titration. The images below show the burette before the titration begins, below left, and at the end point below right. What should the student record as the volume of NaOH aqueous delivered to the flask? So let's look at the volume it starts with. Or we can say the difference in the volume is just going to be the recorded volume. So here we have 37.3, and here we have 5.65. That gives us about 31.65. Yeah, 31.65 ml. And that's how we get this. So that's it. Alright, now B. Based on the given information and your answer to part A, determine the value of concentration of the acid that should be recorded in the student's lab report. Okay, so for this one, we're going to use M1 times V1 is equal to M2 times V2. What we're looking for is M1. And we know V1, M2, and V2. M1 times 0.0250 liters is equal to, because remember we have to convert these milliliters to liters, is equal to 0.110 molar times 0.03165 liters, which we get from here. We get M1 is equal to 0.139 molar. And that is our answer. All right. And for the final question, 7C. In a second trial, the student accidentally added more NaOH to the flask than was needed to reach the endpoint, and then recorded the final volume. Will this error increase, decrease, or have no effect on the calculated acid concentration for the second trial? Justify your answer. So, because of this, I'm going to write this one out. The error would increase the concentration. So the volume of the NaOH larger than the actual volume needed to reach the equivalence point would lead to a calculation of moles of the base that would be greater than the moles of the acid actually present in solution. So that if you assumed that the moles of acid are the same as the moles of the base, that would lead to a calculation that is higher of the acid that would be higher than the actual concentration. So that's just like wrong. So we could write the higher than the actual concentration. So sorry I was quiet then, but I was trying to just think. So the error would increase the concentration. The actual volume needed to reach the equivalence point would lead to a calculation of moles of base that would be greater than the moles of acid actually present in the solution. The assumption will lead to an increase of the calculated concentration and will be higher than the actual concentration. So that's how we solved this. And we justified our answer and we did really well. And yeah, this is the walkthrough to the whole test. So if anyone has any questions, speak now or forever hold your peace. All right. So looks like no one has any questions. So if you guys want, you guys can leave any questions down in the comments below, and we will answer them. All right. So that's it for the stream.